Hello there, Mr. Sutton here, bringing you the AB Calculus 515 Extra Practice Number 5 solutions on integration by substitution with definite integrals. On this free response problem, we're given this graph of f prime, and they also gave us some areas between f prime and the x-axis. And we're told that f of 6 is 7, that might be helpful, and also that g is x squared minus 1. So based on all this, we want to start by finding the value of the integral from 0 to 9 of f prime of x dx. So basically we're just asking about the area under the curve of f prime. So since we're going from 0 to 9, let's start at 0 here. So integral from 0 to 3, because we got to split this up into different areas, that's just an area of 12. And then we have to add to that the area of 10, except that it's underneath the x-axis. So we're actually going to be subtracting 10. After that, we're adding 5 and subtracting 1 for that area under the x-axis over there. So you could leave it like this, or if you simplify it, we have 2 plus 5 is 7, minus 1 comes out to 6. On this problem part, they're reminding us that f of 6 is 7 because we already forgot, and they want us to write an expression for f of x involving an integral, and then use it to find the absolute min and max. Okay, so let's start by getting an expression for f of x. So to find any value of f of x, we have to start with the value they gave us, f of 6, which has a value of 7. So I'm going to write f of x equals 7. And we're going to have to add the integral from the x value 6 to whatever x value you want to input. So I'm going to say plus integral from 6 to x of, and now we're taking the integral of this f prime right here, but here's the catch. We can't write f prime of x because we already used the variable x in the upper limit of integration. So instead we're going to write f prime of some other letter, like f prime of t dt. And this would be an acceptable formula. Just to emphasize, if you put an x in here and also here, it's not mathematically correct because these variables are doing different things. All right, so at this point now they want us to find the absolute min and max of the f function. In order to do this, we're going to have to use the candidates test. We're going to have to test out the endpoints, 0 and 9, in the f function. We also need to check out critical values. At this point, let's go find those critical values. Critical values are going to be places where f prime equals 0, which we can tell just by looking at the graph here. So that's going to be at the x value 3 and 6, 8, and also we'll count 9, although we were going to test 9 anyway because it's one of the endpoints. So now we just have to go through and test the endpoints and these critical values. So let's start with the endpoint 0. For 0, I have the starting value 7 plus integral from 6 to 0. Well, that means we're going backwards, which means that all the area that we would have been subtracting, like this area of 10, we're now going to add. And all the area we would have been adding, like this area of 12, we now have to subtract, just because we're going from right to left if we're doing 6 to 0 to a number less than 6. So then at the end of the day, we're doing minus 12 and plus 10. So 7 minus 12 is negative 5, plus 10 comes out to 5. And the reason I'm simplifying this, again, I'm using the candidates test, so I have to actually be able to compare these numbers, and it's hard to do that if I don't simplify them. All right, let's test out x equals 3. So now we have f of 3, which is going to be 7, plus the integral from 6 to 3. So again, we're going backwards for this. So this area of 10 that we would have been subtracting, we are now adding to 7 to get 17. Next, we have f of 6. Now, f of 6 is an easy one. They already told us that was 7. And, I mean, if you think about it, you're doing the integral from 6 to 6, which is just going to come out to 0 anyway. Next, we have, let's see, f of 8. So that's going to be 7 plus, now we have this area. And since we're going from left to right, this area above the x-axis is now considered positive. So we're doing 7 plus 5 here, the area there. And that's going to be 12. And then finally we have f of 9, which is going to be 7, plus the 8 that we had from 6 to, or plus the 5 that we had from 6 to 8, minus this 1 here. and that's going to be 12 minus 1 is 11. Looking through these, the smallest value out of all of these is this 5 at f of 0, and then the absolute max is going to be the 17 that we had at x equals 3. For this part of the problem, they want us to find the indefinite integral of the g function here. So we're just taking the antiderivative of x squared minus 1 dx. That's all there is to this one. Using the reverse power rule, this first one, our exponent bumps up to a 3, and we divide by that. So that is 1/3 x cubed. Next, this minus 1, using the reverse line rule, we're going to have minus 1x. And then don't forget your plus c at the end, and that's really it for that part. For this last problem part, we're trying to find the definite integral from 2 to 3 of x times f prime of g of x dx. So this looks like kind of a mess. I'm going to start by replacing this g of x in here with the actual formula for g, which is x squared minus 1. So that's, I don't know if that looks nicer or worse, but it's actually going to make our lives a little bit easier. Because once I do this, I notice that I have an inner function whose derivative, which is going to involve just an x to the first power, that derivative is elsewhere in the problem. So if I'm trying to take this antiderivative here, substitution is going to be a good call on this one. So let me let u equal x squared minus 1, and we'll do the u dance here. Let's take the derivative. That's du equals 2x dx. And then we can write du over 2x equals dx. So that takes care of the dx. We also need to change these limits of integration, the 2 and the 3, which are currently x values. We need to change those into u values. So if x is 2, the lower limit of integration, then u is going to be 2 squared minus 1, which is going to be 3. And then if x is this upper limit of integration of 3, well, now u is going to be 3 squared minus 1, so 9 minus 1 gives us 8. All right, we have a whole bunch of things to replace over here. Our limits of integration, we're now going from 3 to 8, and then we still have that x in there. We have f prime of u, and then instead of dx, we have this du over 2x. Cleaning this up a little bit, the x's are going to cancel, and I can write 1/2 f prime of u du. And now we can take our antiderivative. Well, this is actually not so bad. The antiderivative of f prime, the thing I have to differentiate to get f prime of u, is just simply f of u. So we have 1/2 times that from 3 to 8. So let me yank out that 1/2, and I'm doing basically f of 8 minus f of 3, where 8 and 3 are now u values. So we have the 1/2, and what was f of 8? Well, we actually found this back in part B. F of 8 was the 7 that you start with at x equals 6, plus this area of 5. So that's 12 altogether. And then for f of 3, that was the 7 we started with at x equals 6, plus this 10 that we had to add because we were going backwards. So that was 17, and that's what we're subtracting from 12. You could leave it like this because you've got all constants, or since this is -5, you could turn this into -5/2. Either way, we are done. For this free response problem, we have this g function given by the graph here, and then we also have this piecewise f function, the first two values of which are going to be from this weird function, and then g function is handling everything from 2 to 12. So for the first part of this problem, they want us to find the limit as x approaches 5 of g of x, or state that it doesn't exist. Okay, so taking a look at what's going on here, we have to do the inner limit first. So we're doing g as x approaches 5. What is g approaching? Now, at first glance, if you look at this, as you approach from the left and the right, you're approaching different values. So you might be tempted to say that because the limit does not exist for this inner g function, the limit does not exist for the outer function. But we actually do have to break this down into left versus right. So let's tackle the limit as x approaches 5 from the left of the inner g function, and let's just see where this goes. So as I approach 5 from the left side, that's getting me to the value of 3. Now, that means that we're doing the limit as x approaches 3 of the outer g function. But when we're doing this, since we're approaching this y value of 3 from below, when you're coming from the left, you're actually also coming from below. That means that your outer g function is approaching 3 from the left. So the left-sided limit at 5 of the inner g function gives us actually a left-sided limit of 3 of the outer g function. So looking back at the graph, as I approach g from the left side, as I approach 3 from the left side, I end up with an output value of 3. So the left side limit at 5 of g of x is going to be 3. All right, now we have to look at the right side limit. The right side limit, as I approach 5 of that inner g function, is going to end up being 5. Because as I approach 5 from the right side, I'm up here. But now, if I'm approaching 5 from the right side, I'm actually also approaching the y value 5 from below. Since I'm approaching 5 from below, that means that I'm also finding the limit as x approaches 5 from the left of the outer g function. So this is a little bit tricky. It all comes down to, what y values are you approaching from? Which side are you approaching from in terms of up versus down? That's telling you whether you're approaching from left versus right for this outer function. Because the output from the inner g function, the y values from the inner g function, become the x values for the outer g function. So now, on the outer g function, as we approach x equals 5 from the left side, well, here's 5. Approaching from the left, that is actually also a value of 3. And here's the remarkable result. Even though we have this jump in here, because we happen to be approaching the same value from the left and the right, that means that the limit as x approaches 5, the overall two-sided limit of g of x, is going to equal 3 because that's the limit from both sides. For this problem part, to figure out if f of x is continuous at x equals 2, because x equals 2 is a border value, we have to test out the left side limit, the right side limit, and the function value there. Let's do the left side limit as x approaches 2. So that's going to be using this less than 2 rule here, this 3e to the 4 minus x squared. So we can just write 3e to the 4 minus 2 squared. This is just e to the 0, which is 1, so this is all just 3 when all is said and done. So there's our left side limit at 2. Right side limit at 2, well, that's using the g function now. So that's just going to be g of 2. And we can look that up on the graph. That appears to be 3 as well. And we also, in order to get full credit on this, since we're talking about continuity and not just whether the limit exists or not, we also have to talk about f of 2. Well, what's f of 2 going to be? What's the function value going to be at 2? For that, we look at our piecewise function, and we see that 2 is included in this first rule. So we're going to write f of 2 equals next to this 3 here that we found by doing the left side limit. So they just happen to be the same value. But even though there's the same value, if you don't mention f of 2, you haven't actually shown that this function is continuous, only that the limit exists. But now that we've also verified f of 2 equals 3, we've shown that the limit exists, the function value exists, and most importantly, that the limit and the function value at 2 are the same thing. Once you've shown this little line here, you've shown that f is indeed continuous at x equals 2. On this problem part, we have a particle moving along the y-axis with velocity v, where v is really just the same as f, between the interval from 0 to 2. So we're getting some more mileage out of this branch of the f function here. We want to find the acceleration of our particle at time 1 and whether or not the particle is speeding up or slowing down. All right, well, let's start with the acceleration. So the acceleration in general is going to be v prime. And v prime, since v and f are the same thing, v prime is really f prime of x. We could call it f prime of t, doesn't really matter. So this is going to be 3e to the 4 minus t squared times, we have to multiply by the inner function, there's a chain rule going on here, times negative 2t. And now to find a of 1, which is what they wanted us to do here, acceleration at time 1, that's going to be negative 2 times 1 times 3e 4 to the e to the 4 minus 1 squared. So let's see here. This is going to be 3e to the third. We have a negative 2 here, so negative 6e to the third when all is said and done. So that answers the first part of the question. Now they also want to know if our particle is speeding up or slowing down. Now for this, we have to compare the signs of the acceleration, which we just found, and the velocity. So let's take a look and see what the velocity is. Again, velocity is just going to be the f function from 0 to 2. So I just need to do 3e to the 4 minus 1 squared if I want to find v of 1. That's just going to be 3e to the third. Now comparing these, negative 6e cubed is negative. 3e to the third is positive. We observe that v of 1 and a of 1 have opposite signs. Therefore, our particle must be slowing down at time 1, since velocity and acceleration are working against each other. For this problem part, to find the integral from 3 to 8 of g of 2x minus 4 dx, I'm going to use substitution because I have this inner function. I think there's other ways to do it, but this will probably be the most straightforward way. So let's let u equal 2x minus 4, and then that means that du is going to be 2 dx, which means that du over 2 is the same as dx. Also, I have to swap out these x values that I have for limits of integration for u values. So if x is 3, that means we're going to have, let's see, 2 times 3 minus 4. U is going to be 2 for that one. And then if x is 8, the upper limit of integration, then u is going to be 2 times 8, 16, minus 4 gives us 12. Swapping all of that out here, I've got the integral from 2 to 12 of g of u. I have a du over 2 here, but I'm going to pull that 2 out as like a 1/2. So this is my final integral in terms of u. Now I don't know the antiderivative of g of u, but I can just figure out the integral of g from 2 to 12 by looking at the graph and finding the area between 2 and 12 here. So I'm going to have a 1/2. And now for the actual area, I've got an area from 2 to 5 that's just a square, so that's 3 times 3. And then the area from 5 all the way to 10, this is going to be a positive triangle, so 1/2 base of 5 times a height of 5. And then we have this negative area underneath the x-axis, another triangle. This is going to be minus 1/2 base of 2 times a height of 2. So we've got 9, 25 over 2, and we're subtracting, well, these 2's are going to cancel, so just subtracting 2. So then that's going to be 7 when all is said and done, plus 25 over 2. And to be honest, if I wanted to, I actually could have stopped right here this step before because there's all constants. But if you want to just keep simplifying, well, let's see here. This is 14 over 2 plus 25 over 2, which gives us 39 over 2. 39 over 2 times 1 over 2 is going to be 39 over 4. So that is the final simplified answer that you could use.